Today we're going to learn about stress concentrations. Now, most geometries have some form of stress concentration because most geometries have a change in the cross-sectional area. Whether there's a large diameter that transitions to a smaller diameter, whether there is a hole in a part, a chamfer, or a fillet, most real true geometries have the presence of stress concentrations. Now, some examples, we can look at a shaft that goes from a large diameter to a slightly smaller diameter. But other features on that shaft can also be stress concentrators, such as spline lines that allow a shaft to connect to another shaft, or the shoulder where a fillet exists, that the transition from the large to small diameter, or can even be lines on the shaft where gaskets would sit, or where oil grooves, where oil would flow, or even where a bearing would sit on a shaft. Similarly, something as simple as a bolt has a number of features which could lead to stress concentration. The bolt head has a larger diameter, and it transitions through a shoulder where the diameter sharply decreases from the large to the small diameter. And then along the small diameter, there are a series of threads, these sharp features on the surface, which all represent a stress concentration. Things such as this, just simply a transition from one diameter or one size to a smaller size, or even fine surface features, are what we call stress concentrators. Now, what is a stress concentration? How do we calculate the impact of those concentrators? Well, the stress concentration factor, which we denote as a capital T or a capital TS, is used to relate the actual stresses at the discontinuity, so say at the threads, with respect to the nominal stress over the cross-section near the discontinuity. And we'll get to that, we'll get a little more clarity on that in a minute. But the basics of it is that KT, this factor, is equal to the maximum stress at the discontinuity divided by a nominal stress, a net area stress near the notch. And there are two forms of it, one in terms of normal stresses, and then another one, KTS, in terms of our shear stresses, right? Now, what's important to note about these factors, KT and KTS, is that they depend only on the geometry and the type of loading that is applied to a part. The calculation, the measure of these KTs comes strictly from the geometry and loading, and the particular material itself doesn't have an impact on the calculated KTs that we find. So, for example, let's consider a plate with a circular hole. So we've got our plate here. Let's assume that it has, it's infinitely long, so that the ends where we're loading are very far away from the hole. We've got a hole in the center, and then we're applying a uniform stress at the top and bottom of this plate, right? Now, if we were to think about stress, the stress that's applied remotely as a series of lines, we can see that as those stress lines approach our circular hole, they must bend to go around that hole, because a hole is an absence of matter. If there's no material for stress to flow through, then it has to concentrate around the edge of that discontinuity. And so our maximum stress, the stress is going to be maximized at the edges of this hole feature, right? That's the maximum stress. Now, the nominal stress is the stress in the cross-sectional area near the notch. Assuming that stress wasn't concentrated, if we say, if we have stress here over the full area, we're simply calculating the nominal stress as the same force, but over this smaller area, this net area that's remaining. And with that calculation for this particular geometry, we end up with a relationship between the nominal stress and the stress applied remotely to the ends of this geometry. It's simply going to be the width divided by the width minus the diameter of the hole times that remote stress. where then KT is equal to sigma max over sigma naught, right? Now, the determination of the stress concentration factor for different geometries and loading conditions can be difficult. For every geometry, every unique geometry that we can imagine, there's a different KT value that must be calculated from that geometry. There's a few ways for us to find those KT parameters. One is to do derivations, so to use the theory of linear elasticity to derive the state of stress, the equations for a geometry. It's kind of hard to do. Not a lot of people do it anymore. Another way, a good way to estimate, is finite element analysis. This is really great, particularly if we're designing a unique geometry, some kind of unique component, can help us estimate the stress concentration factor. But it doesn't give us an exact value. It's a good approximation, but not perfectly exact due to the elements, the finite elements having a certain size. And then a third method is experimental techniques. And there are many experimental techniques that exist out there where we can actually measure or see the strain field, and from the strain field calculate stress, the stress intensity and certain features. But it does have some challenges or limitations. Now, in terms of FEA, it's fairly simple. You'll create your geometry, you'll put your discontinuity, you will apply boundary conditions of load and displacement constraints in order to constrain your object in space, and then you'll simulate the stress field, and from that simulation be able to calculate what the value of that max stress is, right? In terms of the existing theoretical equations, there is a, kind of a tome, Peterson stress concentration factor. I think it's about 1,000 pages long that includes many hundreds of stress concentration factor calculations from different geometries. A combination of those that are derived from the great mathematicians, but also some that are numerically solved from finite element analysis. Now, in terms of our class, our textbook, gives us a good series of stress concentration factor charts, which we can use and we will use for our homework and our exams. Those charts can be found in section 313, as well as in appendix 15 and 16 of our textbook. Now let's look at an example or two of what a stress concentration factor chart is and how do we read these charts. So for our first example, we'll go to section 313 and we'll find a stress concentration factor chart for a thin plate in tension or simple compression with a transverse central hole. Here we're told that the net tensile force, F, is equal to sigma times W times T, where T is the thickness and W is the width of the plate. And the nominal stress in the vicinity of our discontinuity, the sigma naught, is equal to the width divided by the width minus the diameter of the hole times the remote stress, right? So we've got a lot of good information here that is going to help us solve this problem. Now, in order to find sigma max, the maximum stress, we need the KT value. We need to read this chart and find the KT value. In this chart, we're given two things. On the x-axis, we're given a ratio of the diameter of the hole over the width of our plate. And on the y-axis, we're given the corresponding KT value for that particular geometry. So this chart is basically giving us many different types of plates with a hole in them, and we're able to then select based on our dimensions for a given problem which KT it corresponds to. So say we have D over W, and we find for our geometry that it's equal to 0.14. Then we go up to the line, then we go over, and then we can estimate our KT value as being between 2.2 and 2.3. So a pretty good estimation there, right? So let's look at another example. One that maybe is a little bit more challenging. for this example, we've got to go to Appendix A15. And in this one, we're given a rectangular filleted bar in tension or simple compression. The nominal stress is equal to the force over the area, where the area is taken over the smaller cross-section. So little d times t, where t is the thickness. So we've got the equation for our nominal stress. We want to find sigma max. So now we need to find the KT parameter corresponding to our geometry. Now, in this case, the geometry has 3 dimensions: big D, little d, and the fillet radius r. And so we're going to have to, if say we're given a problem and we know those 3 parameters, we're going to have to read this chart and find the corresponding line for the big D over the little d and the corresponding position of r over little d, and plot up and over to get our KT value. So let's see, for an example, let's say the ratio of d over little d is 1.5, and let's say that the ratio of r over little d is right here in the middle here between 0.1 and 0.125. So 0.125, right? In that case, we'll need to plot up to the line corresponding to our d over d value, and then we'll plot over. So we're sitting just below 2. KT is just below 2, right, for this particular geometry. Now, of course, say we had a different ratio of d over little d, but we had the same r over d, the 0.125, then we'll plot up to that line and over, and in that case, we are just below KT equal to 1.6, right? So that's pretty much how we read these charts. And, say we had some ratio that sat in between 2 of these lines, then what we need to do is we need to plot our lines and find the KT that corresponds to each of those intercepts, and then do a linear interpolation between those 2 points and where we are d over d between these 2 lines. So there's a little bit of work we've got to do if we're in between lines, and we'll learn about that in class in one of our examples. With that said, there is something special we need to consider with stress concentration factors, and that is that for ductile materials, there is an exception. You see, with brittle materials, when you load them up, there's very little plastic deformation, and they tend to just break at the ultimate tensile strength of the material. However, ductile materials, once you get to a certain point, they start to plastically deform. So their shape starts to change where stress is highest, and that plastic deformation can lead to stresses actually decreasing rather than increasing at a notch. And thus, we come to the ductile material exception, where for static loading, if we have a brittle material where its ductility is less than 5% or 0.05, then we apply stress concentration factors. We find the KT or the KTS using our charts. But if we have a ductile material whose deformation or ductility is greater than 5%, then a stress concentration factor is not applied because of that plastic deformation that occurs. And that yielding can lead to a lower intensity of stress at a notch. Now, generally, what we'll do is we'll just set KT and KTS equal to 1, so we don't apply a concentration. But the better approach, is to use finite element analysis to analyze our actual structure and then actually estimate how much stress does concentrate due to yielding, right? One more material that is of interest is gray cast iron. This is a material that can have some ductility to it, but cast iron in particular has many stress razors and defects inbuilt into it due to its cast nature. And so in that case, with cast iron, we also set KT and KTS equal to 1. We don't apply a stress concentration factor. Now, another thing that we're going to encounter when we get to fatigue is that stress concentration factors in fatigue do apply to both ductile and brittle materials, but they're not always applied equally. There is a sensitivity factor for materials depending on if they're ductile or brittle. So when we learn about fatigue, in all cases, we'll need to find our KT and KTS parameter, and then we'll need to take some extra steps to find this sensitivity factor that we can then apply during fatigue. So with that said, we've covered everything that we need for stress concentration factors. We'll see you in the next video.